We have a special treat today. Dr. Tyler Kress is here. I'll give a quick introduction, and then he will give us a fascinating talk on product safety management and the human side of the engineering here in a minute. So Dr. Kress is the president and principal consultant for the Best Engineering Incorporation, and also an adjunct professor at Virginia. He has spent his career as an engineering safety professor and researcher at major universities and served as a director. You'll see this pattern coming up again and again, that he has been in charge of the safety and safety investigation over his entire career. He's a principal scientist and associate director of the University of Tennessee Engineering Institute for Trauma and Injury Prevention. He was the associate director of the University of Tennessee Safety Center and served as the University of Tennessee's lead person for safety, security, human factors within the University of Tennessee and Oak Ridge National Laboratory, National Transportation Research Center. He has conducted research on behalf of major automotive and motorcycle manufacturers, the American boating industry, sports equipment manufacturers, occupational safety and health administration, and various other industries and organizations and corporations. He is an expert advisor to the United States National Transportation Safety Board, also known as NTSB, served extensively as a consultant reviewer for Center for Disease Control's biomechanical grants, and served as a member of officer in numerous professional societies. He consults frequently for various national and international recognized companies, including major restaurant chains, numerous insurance companies, trucking companies, cruise lines, and so forth and so on. Dr. Kress has been called upon to serve as an expert witness in product design and court cases, engineering science and mechanics, industrial engineering, human factors, again, in a variety of roles in various state and federal courts all across the country. He has testified in well over 1,000 forensic cases and has published over 100 scientific and engineering papers. As you can see from his brief bio, that he has done quite a bit of work on behalf of the country and for the state for the safety of a variety of industries and work. So please join me in giving a warm UTC welcome to Dr. Kress.
Well, the first thing I'd like to say is thanks to Dr. Pack and Dr. Nassad and Miriam for putting this together and extending an invitation to me. It's quite an honor to be here. I'm born and raised in East Tennessee. Love this area. Love Chattanooga. Uncle and aunt lived and died here. Still have a cousin here. And born and raised in Oak Ridge, and my heart's with the University of Tennessee for sure, and the whole network. So I enjoy doing anything like this and meeting people at different facets of our great university. I see it all as a nice system that everything complements everything. And you know, everything, I haven't been on this campus very much at all over the years, and everybody I've ever met, I've just thought the world of, and I always hear great things about UTC. I had a niece go here too, and she really enjoyed her experience. So it's a real honor and pleasure to be here. I appreciate it. This is a small enough group that hopefully, I welcome you just to stop me and ask me things or interrupt me or something if you're curious about things. I'm a little curious about the audience, so that I'll cater it a little bit. We have any in here that are, say, computer engineers, industrial engineering type? Two, engineering management type? Okay, civil engineering management type, okay. Any mechanical engineers? Miriam, I think you've got a degree in that, don't you? Okay, just checking. That's the teacher in me. What's that? Civil, I didn't mean to leave him out. How many civils we got in here? Mechanical, you've got civil. Chemical, electrical. Okay, well, I know the crowd here now then. Okay, so my background's a little odd in that I'm heavy into engineering science, mechanics, and mechanical engineering design side, and biomedical engineering. But for my doctorate, I switched engineering disciplines. It took a little more work, but I kind of wanted to expand my knowledge. So I got it in industrial engineering, and I had minored for my master's in engineering management. So I kind of had heavy on the design side and mechanical and engineering mechanics side, and I wanted to complement that with what they do in the engineering management and industrial engineering and manufacturing side of things. So so I'm kind of a hybrid in that respect. And come on in. You're not bothering anybody. If you want to, that is. This might be. So I'm not sure I'll bring too much to the table to you engineering management people, but I'm hoping to a little bit. This is, if I were to categorize the talk with respect to some of the categories I'd seen going on here, this is kind of on the engineering management, human factors side of it, obviously, by the title. All right, let's see here. I can make this little sucker. We got the mouse here now, right? Oh, that was nice. I'll just do it with security alert. Perfect. Let's see if I get this little sucker to work here. It doesn't need it. Okay. I'll get some of the boring slides out at first, so I can feel like I did my teacher role and said a few things. As engineers, it doesn't really matter what engineering you're in. It doesn't matter if you're chemical, electrical, nuclear, mechanical, civil, industrial, engineering management. Your responsibilities are quite huge. I used to have a very, very fun professor. He was very, very strict. He would count off -10 if you didn't dot your I's and cross your T's. No kidding. And he gave a quiz every day. And he used to give these real extravagant talks in lecture where he would come in and he would give an example about an engineering mistake or an engineering failure. And he would talk about how many people suffered or how many people died as a result of that. And he would say, a medical doctor makes one error, one person might be badly injured or suffered, unless they continue to do that error over and over. And he talks and emphasized the importance of the detail of engineering and not making a mistake. And so he was always a fun professor because he always had a neat example, and then he tied it into the equations and the lesson of the day. So as an engineer that works in forensics, and forensics it technically means for legal and typically means for criminal purposes, but it's gotten a broader meaning in the sense that it's for legal purposes. So anytime you, especially in engineering management, if you end up working for any kind of company, whether it's even, you'll at some point have to deal with the legal world. And engineers are often called upon and needed in our judiciary system to help them solve problems and to help them figure things out, because lots of times it's a mystery, or lots of times it's not a mystery, but opposing sides want to make it a mystery. And you have adversarial sides. One says it's blue, one says it's green, and then they like to have the engineers to hopefully figure it out or convince the jury what is the truth. So anytime you're an engineer, if you're working for a company, you may be called upon to represent that company as a corporate representative and to talk about what you did in your engineering management role, your mechanical engineering role, your industrial engineering role, or what the company did and speak on behalf of the company. There's all sorts of things that you have to do as an engineer in your role in making sure you address product safety. And it's not just product related, but I'm kind of catering this talk somewhat to products. It's much more global than that. But you have to investigate accidents. You have to understand how they occur. Lots of times our courts in this system rely a lot on medical doctors sometimes to try to talk about injury causation. And some of them are excellent, some are very good at it. But a lot of clinicians out in the world that are medical doctors, they focus on what is wrong and how do I fix it, diagnosis and treatment. As an engineer who has to manage engineers and manages a workforce, manages design teams, manages manufacturing lines and the quality control, etc. You have to look at how injuries can occur with whatever you're producing or whatever you're doing. And you have to understand all the possible causes and risk associated with that. And you have to make sure that you foresee them to a reasonable degree and you account for them. So understanding the cause end of injuries or death is very, very important for the engineer. Oftentimes, much more important than the doctors. Now, they care about cause because they want to solve it. If something's causing it, they want to get rid of that cause. But their primary focus is diagnose and treat. But sometimes that treatment aspect is trying to figure out what caused it. But engineers especially has to learn a lot about how products fail and how systems fail and where humans are vulnerable, where they're interfacing with the world. So lots of times the engineers need these types of, oh, I didn't mean to touch it, my bad, need these kinds of skills here. Okay, good. So they need to figure out how accidents occur. They obviously need to evaluate the products to the nth degree. This includes not just accidents in dealing with the products out in the stream of commerce, but they have to care about their manufacturing lines, their industrial safety environment, etc. They oftentimes get involved in understanding the details of a medical product too, because again, the engineering behind these things are much better understood by our education and the teams that engineering management people manage, as opposed to sometimes the users. Then this is an interesting little, the last two categories I won't spend too much time on, but I'll touch on them because it's amazing as industrial engineers, as mechanical, as civil, as engineering management, as the things that you get into as an engineer and what you're asked to do when you're having to do your work. So when we think about human engineering, and there's no engineer or engineering discipline that doesn't have to deal with human engineering. I know there's some specialties. You've got the biomedical engineering, you have human factors engineering within industrial engineering, but any engineer, whether you're in any one of the disciplines I've named, you have to deal with humans and be concerned with humans in the workforce, and also people that would be exposed to your company or your business or your product or things that you do. So you have to learn things like how a human interfaces with the world, what their threshold limits are, what's appropriate. If you're a nuke, you know, what's appropriate defense in depth with respect to your design of your reactors, and then how you're going to release it when you have failures. And what are all these things? All of these things are very important elements in any field in engineering, and very important to understand as an engineering manager how to manage your people and ensure that they are relying on the appropriate human engineering data. These are big words in our field. Engineering reasonableness and judgment. A big part of how we're held accountable in this country, in our legal system, and engineers being held accountable, is based on, in many respects, I know we love 2 + 2 = 4. We love the math aspect, and we want an answer. We want to solve a problem as engineers. But amazingly enough, it comes down very often to what one may consider subjective, because the word judgment or reasonableness is in there. And that's a big term that in any industry that you're in, you need to make sure you have a good handle on, and especially in engineering management and managing your people, because there is going to be a time where you may be held accountable, or the people you're managing or work with or team may be held accountable, and you're going to be held accountable for doing what's reasonable. And what I mean by that is we all might have in our mind, based on our own experience or what we've seen advertised or what we've done in our profession, that some cars are safer than others. You know, the Volvo's safer than a Hyundai, for example. So we all have this idea that some things are safer than others. Some have better safe systems. Some you can go out and you can spend $500 on a motorcycle helmet, or you can spend $70. What are you getting for that extra $430? Yeah, you're hoping you get something safer. And it's no doubt you can have the same type of product, but it can be safer. Just because it's safer doesn't mean the one that's not as safe is bad. What we are judged on as engineers in this country and pretty much worldwide is what we did is reasonable. And as you can imagine, the definition of reasonable is ambiguous. There's not necessarily fine lines in all areas of engineering on what that is. The things that contribute to reasonableness is what's the standard of care associated with that topic? Are there regulations? Are there laws? Are there state laws? Are there federal laws? Are there municipalities? Are there laws? Because if you're breaking the law, you're pretty much negligence per se. You screwed up, okay? That's a pretty defined line. That's not reasonable if you're breaking the laws in engineering and you're not compliant to codes, federal regulations. It goes beyond that. Just because you comply doesn't mean you're reasonable. In fact, codes, laws, as engineers, we should consider minimum standards of care. We have to meet all of those. Okay, those are minimum standards of care. So the threshold for reasonableness goes beyond that. And where it goes beyond is what is the state of the art of that subject you're on? What are the volunteer standards that are available? What are the ASTM, ANSI? What's the literature and the science say about this topic? What do we know? And that is where the big rub comes and the big argument comes. And that's where your responsibility lies as an engineer and as an engineering management, managing processes or designs, is what is reasonable to do at the manufacturing line, what's reasonable to do at the design stage, what's reasonable to do at the warning and the use stage. That's the important things. So you get to make sure that you ensure your products through various quality control and assurance in the manufacturing area, fault tree analysis, failure modes and effect analysis, all, cause and effect, Ishikawa, all the different processes to make sure your design is appropriate and you've reasonably addressed the standard of care. You have to know what the thresholds and the safety factors and what are the, I keep doing that, what the vulnerability is for your particular issue you're dealing with. And then you have to make sure that if something goes wrong, or after you've already decided on your design and your processes, if something goes wrong, you better understand it and better fix it and you better address it right. Because you don't want to be the doctor that does 5,000 surgeries and make the same mistake. If you make a mistake, learn from it, fix it, go on. We're all not perfect, we are human. But hopefully you're proactive and you're not reactive. Hopefully you proactively do all this stuff. Okay. So lots of times engineers are called upon to answer questions dealing with accidents. Again, when we're talking about human design, again, I don't care if you're mechanical engineering, designing metal things and machines and parts, engines, whatever your forte is, or you're a civil engineering, designing bridges, roads, substructures, railroad tracks, whatever it may be, or nuclear, building nuclear reactors, electrical, building different electrical systems, whatever you're doing, lots of times the humans interface with all of your stuff and they can be injured. So lots of times as engineers we're asked to find out things. How did it happen? What's the speeds? What were they doing? Were they touching this? How did they get electrocuted? How did they get exposed? What made them die? What made them get badly injured? Who's driving, who's not? Was it a trip or was it a slip? How did they trip or slip? Was it a design issue with the steps? Was it unreasonably dangerous? Was it slippery? Was there something that caused a trip? Was there a Casper sticking his foot out? What are all these mysteries? And there's just, you can imagine the number of questions where engineers are so important because they have the math and the science and the background and the knowledge to be able to figure out a puzzle. So in whatever engineering area you're in, understanding what we are held accountable for in what we do and knowing how to solve the problems are critical. And I think I put fun on the last slide. You get to be a private investigator, but you get to use your smarts and you get to use your education and figure things out. And lots of times when you're going out and investigating an accident, especially if it involves lawsuits, it's amazing how many stories you can have. And your obvious goal or your objective is figuring out the truth and what does the science tell us. And the science can tell us who's lying or who's not. And somebody might not be lying. They may just be making a mistake. You know, especially if they got their hand cut off or something. You know, traumatic experiences, lots of things happen. People make mistakes on what they observe or not. But your job as an engineer is to figure these things out and to answer the questions that need answering. I threw this in just for fun because I'm spending too long time rambling and on boring slides, and thought I'd throw that in just because I think that's a fun slide. I took that picture when I'd been up way too long doing some work, and just curious, anybody have a guess what that is? Just because it's fun, wakes everybody up. It's a dime. Okay. Yeah, it's a dime. Oh, yeah, okay, what's that? Y'all don't know what a dime is in here? What's the deal? So no, yeah, what's the one on the left? I'm sorry. Yes?
Piece of bark.
That's a good guess, actually. It's not. It's not a piece of bark, but it's a good guess. What's that?
Chocolate. A fossil.
You're gonna kind of wince when I tell you what that is because you said chocolate.
Wait, is it the
Give me a hint.
like the
Broken tree.
I'll give kind of a hint in case anybody has a little medical background. See the little Honda? So when we know a failure of me on this. So see the little H in the middle that looks like the Honda logo kind of?
Oh, brain.
Who said that? Dr. Assad, Ed, you said that. Yeah, this is a cross section of your spinal cord. So cord, take a little cross section, and that's about mid-spine level. It's I think, if I remember right, that was around the T8, T9 thoracic middle. So this gives you an idea of just how frail we are as humans. Now I say frail, it's got a lot of bones around it, got a pretty cool column going on, but that thing runs through 24 vertebrae and a bunch of joints. The back's a bunch of joints. You know, our knee's only one joint. Our back is a huge amount of joints. That thing runs right down the middle of it. So it's a wire. It's an electrical wire. So it just kind of gives you a perspective of, in many respects, the frailty of the human and the importance of understanding the potential for injury. I just thought that hopefully also wake you up and see how many people knew what a dime looked like. So I'm going to get into the product safety management side of this for a moment here. As engineers, we obviously deal with products a lot. We deal with consumer goods, sports products, exercise machines, PPE. Vehicles are a big deal, and I might go into some detail on some vehicles, tools, and other machines. And we have to understand the complexity of these products, hence the little silly picture I put in there. So we have to understand to the nth degree, obviously, the detail of a design. If we are the product designer and manufacturer, if we are the company that produces it, we are the experts on that product, and we are held accountable to being the expert on that product. And I've served as a corporate rep for representative in court for a company I didn't even work for, and believe me, when you speak on behalf of a big company and you're making statements based on what they've done, you know when there are people spending tons of money to check to see if you did your F equals MA right, or see if you did your statistical right, or you kept your records correct on the quality control, or your manufacturing processes and systems are the way you were taught in class. And that if they ram your textbook up your rear and say, you didn't do this right, believe me, you will understand the importance of understanding the details and the complexity of whatever it is you're producing because of what we are held accountable for. So this is a big wordy slide, and I think Brian might end up putting these things online. I'm not going to bore you with all these words on the slide. It's what I would tell the students when they give a presentation. That's an awful slide. Don't do that. It's like the horse slide. I love it when they'll have a horse up there, and then they'll label it horse, and I'll say, I know that's a horse. I'm not 3 years old here. So anyway, I'm criticizing my own slide, but These are actually 6 axioms I put together because it may be used or something, but these are, if you were to go out and read bunches of books about product safety management and standards associated with that, and this is essentially what the academic model would come out to be. I put these together based on doing that. So in short, the first one, it's the whole hierarchy. You've heard it before. It's nothing new to this group, I would think. Design, guard, and warn. It's a fancy way of saying it in 6 wordy axioms here. So the first one is all about design. Again, to as far as possible, foreseeable hazards will be reduced to acceptable levels through the design process. Again, foreseeable is a big word. You got to understand foreseeable. And guess what? As engineers, you can't just you're not held accountable just to understand foreseeable hazards that are normal or foreseeable uses. You have to foresee misuses. You have to account for how people may use your product wrongly. Because if you have a product and you haven't thought about all the possible ways it could be used, like getting a piece of electronic, a new stereo, and you see that little packet that says do not eat, and people think, oh, that's a pack of chiclets or something, and they're going to eat it. You got to account for that kind of a thing, believe it or not. So that's important. To the extent you can't design hazards away, you need to guard against them somehow. Design and guard kind of overlap in many ways, because guarding is just a way to design something, but you try to design it out if you can, then you guard it out. Here's where we get into the IE and the manufacturing side, obviously, and heck, you got all the engineers will deal with manufacturing lines and the way they're designed, but you have to make sure that once you've designed it, that it gets made the way you designed it, because you could have a design defect or a manufacturing defect, and the manufacturing defect can be a disconnect from the design or bad quality control processes or what you're doing on the line. Next one's much more important than you realize. I basically say design here, I say guard here, and then down here I talk about warning, but I've got a couple in between that are very real axioms that we're held accountable for. If you are any reasonable sized company in this country that puts out products that have the potential to injure people, there's a lot of products that are more dangerous than others. I mean, if you ride motorcycles, if you use snow skis, all sorts of different products that involves risk, especially if it's recreational or sporting. Juries in this country and our courts want to see you testing stuff. They want to see testing. They want to see that you validated the performance of it. It's okay, it's good, you should always do your equations and figure things out, and you should make sure your manufacturing processes are to the right specs and making things the way you do it, but you also better test it. And you better preserve that test, and you better be sure of it. Look at our drug industry in this country. If you have a certain level of approval at the FDA, they require all sorts of testing, a bunch of clinicals. Well, this is true for any kind of widget you're going to put in a stream of commerce that could potentially hurt somebody. Jurors expect engineers to have tested what they finally put together. And then lastly, this is all the verbiage dealing with warnings. Once you've exhausted all the other stuff, design's the first thing you do, guard's the next, and then last but not least, if you just can't warn it out, if you can't design it out, you can't guard it out, and it's a latent hazard, something that isn't open and obvious. There's certain things that are open and obvious to warn about. Then you should warn about it to the extent as you can succinctly. You don't want to overwarn. Warning is kind of a last tier thing. And I've put in here, and I'm not going to spend the time on this because I wanted to get to some more fun stuff, but this tells you a lot of what I was saying about having to understand potential users and use and the use environment. That includes misuse. You have to understand the lifetime and degradation of your product and address that. You can't just rely, you don't want to just rely on a statute of repose for some state that says after 10 years you can't sue if this product fails. You need to think about it from a human standpoint, but you also need to think about it for what you're held legally accountable for. And then things that you need to make sure you do on the production end, and then obviously the things you need to do at the use end. And this monitoring is important too. You need to be aware of what's going on with your product in the field and keep pretty decent records, because if you don't, it can come back to bite you. And if you keep records and you don't do anything about it, that can come back to bite you even worse. Okay, I thought I would touch on this one because it's kind of an interesting area, and it kind of puts a little bit of engineering in perspective in what you have to do in the world. And I'm going to go right to the center bullet on back injury. I just threw back injury in as an example. We have to deal with lots of kinds of human injury. Back injury is a common one in our workplace. It's a common one that engineering managers have to deal with, and human factors and industrial safety people have to deal with. And there's three main areas in our country where our workers fall into. Workers' comp. Our country decided people get hurt at work all the time. It's just going to happen. And we decided, gosh, our courts would be a nightmare if everybody that got hurt at work had to tie up a court arguing about getting compensated because it wasn't their fault, it was their fault, it was the machine's fault or whatever. So we developed in this country a system of workers' comp where once you become a certain size company, you have to buy insurance, and there's a no-fault deal. It doesn't matter if it's your fault or whose fault. There's kind of the premise that people aren't going to be hurting themselves on purpose to get paid. So the premise is it doesn't matter whose fault it is. If it's determined it was caused at work by something at work, then workers' compensation will help foot the bill for the lost wages and the medical. Two other areas of where workers don't fall under workers' comp in this country. One of them is called the Federal Employees Liability Act. That covers all our railroad workers. They created a new law for them. For those of you that might go into railroading, there's a pretty big presence here in Chattanooga of Norfolk Southern. But they created a whole area for them because around the turn of the 20th century, your average life when you started working for the railroad turned into 7 years after you started working. So it was a really dangerous profession. So they decided we need better laws, not just this, to address the hazards here. So they developed the Federal Employees Liability Act that is a claim. You can do claims within the railroad, but it's if there's any negligence whatsoever, no matter how small, that caused or contributed to the injuries, then the railroad's held liable. So this area is litigated often in this country, and so is the maritime. The maritime has a thing called the Jones Act, which is equivalent to the FLA. There's differences, but again, it's another act to cover those people that work in the maritime industry. But these are the types of things that engineers, you have to be familiar with whatever area you go into, whether it's the occupational safety and health standards, and even in these areas you need to know the OSHA standards because sometimes those are used to establish standard of care. And sometimes those are used against your products, whether your product is a railing, the details of a railing, or your stairs, or whatever they may be. I'll get into some other examples later on. And I'll go through some of these fast because a lot of people like the car example. So I tried to pull together some slides associated with a vehicle because it's a classic product safety management example in this country where, if you would have said in the courts in the early 90s, well, he backed over or she backed over that little kid in the driveway, you should have had a camera on the back of the car so that they could have seen the little kid. We would have laughed at you if you'd have tried to held automobile manufacturers to a reasonable degree of, to a standard of reasonableness that they needed backup cameras there back in the 90s. And if you tried to say they needed seatbelts back in the 40s, they would have thought you're crazy. So, but nowadays, if you bought a car that by 1940s, 50s, 60s, 70s standards, it's terribly defective by today's standards. So we've appreciated incredible advancements over the last century plus in the automotive industry. And random olds, Henry Ford, the whole Industrial Revolution, internal combustion engine, what they did to make them affordable, mass production, and the things they do on the production line, it's a classic example of an evolution of a product. And while lawsuits can frustrate you and you can laugh at them, they can be frivolous, it's important we're held accountable as engineers. We would not even, it may not be the most efficient system in the world. We at least have a system that we've seen remarkable advances in this country because we're held accountable. And but for some of the us having to be drug into the courtroom as engineers, we wouldn't see a lot of the advances that we do, and to make sure that you're, as Dr. Scott would say, crossing your T's and dotting your I's right. And this kind of puts the perspective, how the importance of engineering in perspective. You know, this gives you a comparison of how many Americans are killed in wars versus how many are killed in car wreck. Again, this is just car crashes. I'm not talking about boat crashes or, you know, personal watercraft or airplanes or anything else, or being caught in machinery and things like that. This all goes to, again, where the engineer is responsible for this, and I bet most people in here have heard this, the whole accident pyramid. I guess it was William Heinrich, some decades ago, developed this accident pyramid or safety triangle where you have, anytime there's something going on that may be wrong with your product or may be wrong with your environment, like maybe there's a little quarter-inch discrepancy in where this carpet's lined up here. You don't really see it, but a quarter inch or a half inch is just enough that people don't see it, but if they land their foot right, they trip. So whatever that may be, if I'm walking through there and you got a bunch of people walking through there, you can have a lot of near misses. People step over it, some people hit it and stumble, and then sometimes you might have a minor injury, they stub their toe and break their nail, or they might have all the way up to where they fall, break an arm, or they fall and they crack their head open. So anytime you're getting into this realm, oftentimes you've got to suspect there might be, if it's something wrong, there's you got to suspect these other things going on with your product. And now I'm gonna advance through these. I put these in here in case we wanted to go into it, and I wanted to get down. Oh, I'll go ahead and show these. A simple design principle. Okay, very simple. We see how great our airbags and our, I mean, it's, by the way, if you look at that fatality curve in this country, it's actually gone down some now in the number of car crash deaths per year. You know, we're dropping down to 30,000 now. Back in the 60s and 70s, a heyday, you know, we were up to 50,000 people getting killed in crashes. But we've improved on that. A lot of it's due to the airbags and the seatbelt laws and different things of that, and using the safety systems. But you know, here's a very simple engineering design thing that we haven't implemented, and there's a variety of reasons why. I won't get into all those details, that discuss the principles of engineering being applied to a product in a very simple way, where the stress on the human body is going to be the force divided by the area. And you saw that little bowling ball example. You know, lots of times an attorney will start asking an engineer, they'll go, well, how much force does it take? And I said, well, it depends. And they say, well, how much force does it take to hurt the person or kill them? And I'll say, well, it depends. If I'm stabbing you with a Nerf sword, it's not going to hurt you. But if I'm stabbing you with a knife, you know, the same force would hurt you. So this area is very important. That's why I do that bowling ball example. Anybody in here could take a 10-pound bowling ball and they'll set it on their hand, no problem. Then if you ask me if you let me stick a knife handle in the hole with the point going down, you won't want me to set it on your hand. So it's a very simple engineering principle. These are the types of principles that you're held accountable to and applied. This is our common day seatbelt, where you've got a 3-point belt where it's anchored here and across your chest. You know, you can take that and do that, which they do in some areas, and racing and things of that nature, and it significantly, by 2, decreases the stress. It's a very simple example. But it's amazing how so many of these simple examples can sometimes be overlooked. And if the technology is there, but there are functional reasons why you may not want that, then we're often held accountable for not considering simple design changes that can significantly increase the safety. Now you may ask, well, how come cars don't have this? Go back to that slide where I talked about reasonable. This is reasonable, especially with airbags. I mean, all passenger vehicles in this, you know, sold in this country had to have airbags by 96, 97. You have that in complement with the airbags, that's reasonable. And it's much more comfortable to deal with, and having to deal with that too. And people tend to maybe put that one on more than the other one, so the use goes up. So you always have to consider the big picture. You can't point design things out. And that's important in product safety management. And I'm going to skip over this one. And I'll go to this one here if I can learn to go backwards. Let me see. I'll show you. I had to get it's before lunch, so this is real nice for me. But this will make you appreciate what I just told you about the stress on a human body here. That's an obvious seatbelt from a forward deceleration of that person. And depending on the angulation, the thin edge, the nature of the webbing, whether it has pretensioners or not, whether it it's all about decelerating the human over time. There's all sorts of intricacies that go into design the webbing and the retractor and pretensioners, etc., on dealing with that particular force on the human in a car wreck. And also, notice how it goes over his collarbone and shoulder here. And there's systems like this rely on your bony structure. If anytime kids are bad about this, they'll sometimes lift that seatbelt up and it'll be up here above their pelvic bone. You don't want a seatbelt up there because it just smashes right in and tears up your liver. You need it on the bony structure. You need it down low. And you don't want it going across your neck, or you might end up getting some injuries where you don't want them on your neck. Also, that could be quite severe, knowing the size of that spinal cord, and only gets smaller when it goes up. All right, let's get into a few. Probably don't want to moon everybody. Skip those examples and we'll get to some of the fun here. Actually, I'm going to end up mooning you after all. I'm going to go back to this slide, talk a little bit about it, and then show a few things. I got about 10 more minutes here, and I'll wrap. The slide I had up here, there we go. Often as an engineer, and this is the kind of thing you troubleshoot on a manufacturing line as an engineering manager, the kind of things you troubleshoot when you're investigating the performance of your product out in the field. You got questions of, did the product failure cause it? The whole chicken egg or not. Or did the wreck cause it? I can't tell you how many things I've investigated. Unbelievable amount, not just in law cases, but in research and stuff, where, after an accident, lots of times things are broken. Humans, products, vehicles, motorcycles split in half, people are dead, they're not around to tell the story, and you have to work backwards as an engineer to figure out, just like you do trying to solve problems on a manufacturing line when you have failures and you have a lot of things going wrong in your QA, a lot of rejected parts, or what is causing these things, and you have to troubleshoot it. So I thought, lots of times people like to hear some examples of things, so I just threw down some that I thought might be fun with regards to some product examples and some of different cases that I have experience in, to just talk about some of them, so that you can help put in perspective on what we engineers get held accountable for as a company, and then what you do when you have to come in as a consultant and evaluate these things. We've talked about restraints quite a bit. Burger King, I threw that up. I have no doubt everybody in here has heard of the classic, famous McDonald's lawsuit. Most people go, oh, yeah, burnt coffee, hot coffee. That's kind of open and obvious hazard, hot coffee. It's an interesting case. A lot of people don't quite know a lot of the details of this case, but what the arguments were by the plaintiffs were design. Bad design, too hot McDonald's. You served it too hot. You can't, and you think about it. We know we can get something too hot. You can have it the temperature of molten aluminum. You pour, well, coffee wouldn't get that. It would evaporate. But you pour that down your throat, you're in bad news. So that was one of the principles. Bad design, too hot. Another one was it's just served in this little clear cup. If you're going to make it that hot, and you think it's that important to make it that hot, well, then at least tell the people, warning, it's terribly hot. It's just, don't take a sip. It'll just melt your tongue off, or whatever warning you feel necessary. But, there are serious standards, there's ANSI standards on warnings that you have to follow, what you need, the alert word, and the appropriate identification of the hazard and how to avoid it, and the right font and colorization. They prevailed against McDonald's, big part because I think part of it was because the McDonald's corporate rep, I've read that whole trial. The McDonald's corporate rep was a bit callous and basically kind of discussing the engineering of it. And go, hey, you know, we've only had 700 bad burns or what, you know, throwing out statistics. And in the grand scheme of things, it might be minor to him, but to the 12 people on the jury, it sounds pretty bad. And again, this just shows you may have a winning case, but if you have a bad engineer or an engineer that doesn't represent it well or is smug or doesn't take the job seriously, you can make a jury mad. So the Burger King example, I worked on a fun when I was in the right place at the right time and got to work on a case right after McDonald's suit happened. They hired the same experts against Burger King, and it was a whole lot of fun. And I did tremendous amount of work to understand the science of brewing coffee, why you need to bring it up to a certain temperature for flavor and for making it taste a certain way, why you need a certain temperature because some people put cream in it and that brings the temperature down. Some people like it this hot, some people don't. So there's all sorts of reasoning for science and use as to why coffee should be a certain temperature. And I had a lot of fun because I went around with a thermocouple and collected cups and let Burger King buy my coffees for a year and had this big statistical database. But it's, again, that case puts an exclamation point on because it's in many ways so frivolous about the importance of it. The verdict got way reduced from what the jury came down on. I'll hit on a couple of other examples. Baby changer. Everybody knows the baby changer. Everybody's been in a bathroom whether you have a baby or not. You've gone to a bathroom and you've seen the little koala bear and the koala baby changer. I was reading the president's, the two guys that started that company. I was reading their depositions in a case I was working for them on, and they were being, it's interesting how that company started. It was two guys having a beer in a bar area of a bar/restaurant, and there was some lady next to them changing a baby's diaper, and they were like, God, that doesn't make my beer taste like crap, you know? And so they got out a cocktail napkin and drew this little, why don't they just have a little table that folds down in the bathroom, and before you know it, they're multimillionaires. But they did get sued, and they got sued because a lady went into a bathroom to change her baby's diaper. It happened to be installed inside a stall. So she opened the door, pulled down the thing, set her baby on it, and then she wanted a little privacy. So she decided to try to close the door, and the door wouldn't make it by the changer. So she lifted the changer up a little bit to get it by. And when she set it down, the little baby's finger was in the gap. And crushed the baby's finger, lost the finger. So they got sued over that, and there's lots of questions that they had, and that, you know, again, a design issue that, and they, you know, they called me up and they go, can it crush, we don't think she's telling the truth, can it crush a baby's finger? I said, yes, it can crush a baby's finger. Just with the weight of a baby? I said, yes. So I ended up doing tasks, crushing fingers. But there's all sorts of reasons to crush fingers. Because windows in cars, automatic rolls up windows. Anytime you walk on an elevator, we've all been hit by an elevator door, or you stuck your hand in there to stop it. Those are all design things you have to account for because that people are going to do because they want to get on the elevator. They're going to try to open it, stick their hands in there. You don't want it to crush their arms. So these are all design principles and things that there's lots of voluntary standards and lots of codes. But I brought a couple of other examples. I'll show a few videos at the end here, wrapping up. But here's one that you would not think. I brought a couple I'm actively working on right now. You would not think that something like this, a simple saline bag for surgical use or for patient, that there's a lot of things that engineers have to think about with respect to designing a bag full of salt water on what the hazards could be. And why does an engineer have to think about this? Well, because you hook up tubings to it, you hook up valves, so it's a fluid mechanics problem. You got these little rolly things and these stopcocks, mechanical engineering problem, and then you've got a certain amount of air in there. Why do we have air in there? Well, there might be reasons for air. Might be a variety of reasons to keep the solution a certain way. But if there's air in there, can that get into the human and cause an air emboli? How do we design this to keep it from getting into the human? What do we do? So there's just an amazing amount of engineering in something as simple as a bag of water with a tube. You can imagine the fluid mechanics and the different things you go into. An example of product safety management, I'll show this. This will be the last thing here. I'm currently, thought I'd moon you all again, wake you up. I'm currently working on this project here. This is not a subject accident, but it's a similar accident. Chicken and egg. We have and the amount of time and effort we've had to spend on this, troubleshooting this. We have on the manufacturing line, simple little thing. One of the steering fittings wasn't torqued right. We figured this out. I'm working for the manufacturer of the boat. It wasn't torqued correctly. Simple as one little nut on a steering fitting wasn't torqued correctly. Now, we have a torque spec. That spec has a factor of safety on it. We figured out it wasn't torque spec correctly when I was looking at the boat and figured out where exactly it was based on some evidence. And what happened is these 3 guys were in a boat, actually, I'm sorry, 4. They were in a boat and they hadn't had a lot of experience in boating. They'd had about a year, not been out on it a whole lot. They'd had a lot of experience at drinking beer that day. And they're having a lot of fun getting that boat up to good speed, and doesn't take much. You know, we've all been over a speed bump in our car, and you go over a speed bump 20, 25 miles an hour, you go over a 1.5, 2 foot wave in a boat. It's amazing when your roadway changes in front of you what can happen. So they had what's called a big bow steer. Boat jumped up, hits the bow, and buries it and makes it rotate around. Now, they claim, the plaintiffs claim, that this torque that wasn't torqued all the way caused the steering to fail. That caused this crazy bow steer, and caused the accident. Makes sense if that torque is such that it just randomly will fail during normal use. Even though it was below spec, it wasn't where the spec was, it was high enough that the normal use and what was going on would not have caused this to just randomly fail. But jumping over a wake, burying the boat at an angle and doing this big bow steer where you force a bunch of water into the outboard and in the steering mechanism is enough to bring the pressure up to cause it to fail. Chicken and egg. Did the steering fail first and then the bow steer occur? Or did the bow steer occur and then the chicken and egg? As engineers, you can imagine the amount of effort has had to go into figuring all this out, looking at the manufacturing line, what the specs are, what they're doing, how this happened, what happened, and then the reconstruction associated with the bow steer. Now, I'll show this example here, if it'll behave. Huh. Well, I know how to, it should have been tied to the slide. Is that the... Yeah, we'll just do it brute force way. So I had it tied in there where I was supposed to click on it. All right, so I'm running over time. I'll try to hurry here. All right, it's 5 minutes, but I'm gonna go to the fun part. So we all know what a kill switch is on a boat. Okay. A lot of us don't use them. A lot of us don't use them. You might use them after today. The kill switch, you know, it's like if you ever rid jet skis, you always almost wear them on a jet ski. It's that little lanyard that attaches to the key, and so that if you have a wreck and your velocity changes from the velocity of the craft, and you start to move away from the helm, it kills the engine. That's a kill switch. This guy was wearing his in this incident. He got thrown in the water. He got knocked out by hitting his head on the side of the boat. And the life vest popped him up and brought his head to the surface of the water and had his head upright. Again, a design of a life vest. Simple thing that you think, well, people wear it because if they fall in, they won't drown. Well, what if they fall in and they're knocked out? Then you want to make sure that your life vest hopefully brings their mouth above water if they're knocked out so they can still breathe. So these are an amazing amount of things you need to think of as an engineer. So he's he's tooling along here, and let's see here. I'm getting close to, let's see. So you can see he's coming up to a wake here. Not that big of a wake. You know, again, like a speed bump in the road, right? That's what happens to him. Now I'm going to slow that down a little bit so you can see. So this, he goes up, the front end hits hard, and he takes a pretty heavy bow steer, and then he gets thrown off this end here. He gets tossed over, his head hits the side of the boat, and then he goes in head first, and you can see he's going in head first, right where that motor is. Right where that motor is. Okay. He had his kill switch on. Okay. He's fine. Okay. They do a little slow-mo here of it, showing the. Yeah, they even said here, Greg's life was saved by the kill switch in the vest. So let me go back, and you can see it in slow-mo here while I. Now this was, not a steering issue, obviously. This was a jumping. You can see now where he hits his head, and then he comes over, and he could have hit his head on the skag or the prop too. I don't know that, obviously. All right, just for kicks, because it is very close to your Thanksgiving break, I thought I would end on some tests that I did day before yesterday up in Detroit on this very case. Not his accident, but the one I told you about. One of the many questions in this case was, would the kill switch made a difference in his injury? There's a professor out in North Dakota, I went up to Fargo and I listened to his deposition, who says it won't make a difference. He gets into the engine within a second and a half. He does all these calculations on how, by the way, that one was about 6 seconds. Okay, and that was pretty serious, slung out of there. But he comes to this conclusion that he gets into the engine after about a second and a half, 1.3, 1.4 seconds, and that killing it doesn't make a difference. The prop's still spinning. When you pull a kill switch, it cuts the engine off and loses the spark within milliseconds. So what's spinning? You no longer have the drive of the motor. What's spinning is the inertial effect of a prop. So I sat down, started calculating that. I don't know the exact moment of inertia. I estimated it, and then I did an experiment to figure it out. But I figured out what that is to figure out what kind of injury you're going to get when the motor's not engaged versus when it is, even if it is in the second half. And they contend that the motor keeps running, the thing keeps spinning for 6 seconds but it's a windmilling effect in the water. And it's just the inertial effect of it spinning. It's like when you stick your hand in a fan, if it's driven by the motor, it's going to hurt more than if it's about to wind down and you touch it. So I was so convinced in my opinions, which I have to testify to Tuesday, in my calculations, that I said, we ought to do something demonstrative, because this guy's wacko that's saying, he's wacko, but he's just mistaken. Okay? The nice guy, this professor, he's just made errors in analyzing this accident. And would a kill switch made a difference is a big question here. So I say yes. He says no. I said, well, let's just show. Now, I tried to get some students to volunteer, but they weren't up for it. So I decided, since it was Thanksgiving, to use turkeys to demonstrate it. Turkey's about the weight of a human head. Go get a 10-pound turkey and show what a kill switch does when you do it with a turkey. So right here, I set up an experiment. There we go. All right, what you're looking at here is I got the motor. The boat was going about 35 miles an hour, and the evidence is about 4,800 RPM. So I got the motor going to 48 RPM. So this thing's turning 4,800 revolutions a minute. So obviously this is a high-speed video, or you wouldn't be able to see this. And The gear, well, it's not, that's not turning that, I'm sorry. There's a gear ratio. It's turning more like 2,300 RPMs, okay? But the motor itself, 4,800 RPMs. So there's a gear ratio. This sucker's turning about 2,300. So right at 1.9 seconds before the turkey gets to the blade, 1.9 is when this pull switch was pulled for this test. So it may spin for 6 seconds, but let's see how the turkey gets hurt. And there's dressing. I put gap filler in there for those of you that are concerned. You're welcome to come to my house for Thanksgiving. All right, so you can see the red dot, I put the little dots on there. The red dot mix, the green dot hits. Okay, that's one strike, okay? And it happens to hit the wing. And now the blue dot's coming in. And notice the spread on these dots. It's about 4 inches of spread there. And then we come in here, and wow. I had said that I think on a human skull, the first one would probably not break the skull before we did the test. And I said, it's not going to go beyond 1 or 2. So you could see on the second one, here we broke a little 1/16 inch cortical bone in the wing. Here we got about a 1/2 inch depth of muscle, went through the skin and muscle damage. And it stopped. It stopped it. So now you can imagine the comparison here. So exact same test. This time I didn't pull the kill switch. So I let this thing stay at 23 RPM. By the way, in 1.9 seconds it went down to about 900 RPM. Again, zero torque though, zero torque. So you could see the inertia brought that turkey up a little bit, but the blade brings it down quick enough. 1, 2, 3, 4, 5, 6, 7. Who needs an electric knife when you've got the turkey shooter? Who needs a salad shooter, right? It's obliterated. It's obliterated. Just exact same timing, exact same setup, just simply using the kill switch. A safety feature that some people obviously don't use. And if you want to look at here, I'll show you if I can get over here, show you the last slide that shows the 2 turkeys after the test. Okay, so actually I ran this one through twice. The first one we had 2 little lacerations because it wasn't in the fixture deep enough, and then we fixed the fixture for both of them. All things the same except the kill switch pulled here. We broke a wing and a little 1/2 inch muscle damage, and this one, 17 major fractures and multiple comminution just annihilated. So it again shows a simple difference of a kill switch, even though the person went from the helm to the motor. In this example, 1.9 seconds. So little things can make a huge difference in product safety management. But anyway, I went over. I appreciate your all's attention. Sorry I went over. So I entertain any questions or anything y'all might have. Yes, sir. Yes, Dr.
A lot of the engineering students usually are very excited about inventing things.
Yeah.
And they do invent it, and sometimes they make something and they want to put it up for sale, and they put it on the internet site, and they want to sell that or make a big name out of it. What kind of liability do they have to worry about when they use something like that?
Huge liability. As far as whatever they decide to do and put out there, they need to have definitely addressed all the foreseeable uses and misuses and make sure that they've designed it such that those are addressed to a reasonable degree. You can't design, obviously, the sharpness out of a knife because that's its functionality, or the hotness out of a stove. Those are obvious hazards, but you got to have them. That's the way it functions. But they need to make sure they have reasonably addressed all foreseeable hazards through uses and misuses. And whatever the product is, if there's any, obviously, any codes that law they need to follow, they need to rely on all the various standards available wherever they market it. In the U.S., we have a lot of voluntary consensus standards, that really form the basis of the standard of care arguments in our courts. So ANSI standards, any kind of ASTM, all the zillions of different standard organizations put out these SAE standards. You need to know those inside and out and make sure you've complied with those. And if you haven't, you've got a reason why you didn't, or exceeded or did something else. And then you need to make sure that if there are any hazards that are not open and obvious that are still exist that you feel need to be warned about that you couldn't design or guard out, you need to make sure you do that. And as a person starting a business, I would certainly advise getting the help of people engineers that have been in the product safety world for a long time, and an attorney that specializes in that too, before you start making your widget and selling it, because it very rapidly can go bad for you. I can give you countless examples of simple engineering mistakes on tons of products. A lot of products start like the koala guys did. A lot of products start, I can over and over, not the proper industrial engineering human factors issues, like a little hovercraft thing I worked on years ago. They didn't address he turned it and the throttle hit the cabinet and tilted him over, and he didn't have any legs, hit his head. Just simple little ways to guard controls and to guard. I worked on a huge case for Case that makes backhoes. They were working on a farm, and they were using the backhoe to do some things. He took the chain that they were using and he walked up and he set it in the cab of the it was a front end loader / backhoe. And his dad was driving. This guy was a 30-something-year-old engineer, civil engineer. Just took the chain because they were done with them and set them inside. He set them right inside, right where the pedals were that controlled the mechanism, and it swung right around and crushed him and killed him right in front of his family. And so a lot of things like that. You just need to make sure that you be very diligent with the design process, and then that you ensure that it's made to your specs. If you go ship it off and have it done cheaply in Mexico or China, you better make sure when you get it back it's being made the way you designed it. And if you get to any reasonable size, you better test it. And not all products are created equal. Some are a little simpler than others. A button, for example, or something. But although it has its choking hazards and things like that. Good question, though. More questions about anything? Yes, sir.
You've done, it seems, a lot of things in the field. I'm just curious, where do you start your professional career? What did you begin doing right out of college?
Well, I got into this a lot because I was fascinated in biomedical engineering. What got me interested in biomed is when you think about engineering. I liked mechanical, I liked civil, I liked chemical, I liked electrical. I liked them all. I thought, well, what has them all? And the human body has them all. And it's probably, arguably, the most sophisticated design that exists. It's got a whole electrical system that makes everything run. It's got tons of mechanical systems, motors and hinges and pulleys and all over the place. It's got civil system. We chemical plants, chemical engineering all through there. We eat, we process it. We've got all the hormones and all these systems. We got the most complex materials. If you're a materials engineer, the anisotropic, viscoelastic, composites, that can change with time without an engineer putting a screw in it. It can actually remodel itself. So it's a fascinating engineering design. So I got very fascinated with that. And so I got into getting into research and understanding human injury. I started doing a lot of cadaver research and beating up on dead people. And again, that's one thing you want to do. If you're going to make a helmet to protect a human, I can't get a student or I can't get human volunteers to go out and get hit by a boat motor. So the next best thing is cadavers. It's not lunch conversation. Sorry, it's right before lunch, but that's the next best thing if you want to understand tolerances of the human body. So I got into it that way, and I got very fascinated by designing for the human and how the human interfaces with the world. And then I realized how important also the industrial engineering and engineering management side it was. Because I was all hardcore into the design and understanding the mechanical engineering, engineering mechanics aspect of it. I said, I want to know how all these things are made, whether it's a helmet or protective equipment or an airbag or it's an artificial hip that somebody puts in there. What's the industrial engineering side and engineering management side to bring a product from concept to commerce? And that's what got me. And I just started in grad school, working in grad school, ended up just being a full-time teacher out of the result because I was getting a lot of research because it's kind of a fun area, and that's how it all, and then you started consulting and built the practice that way. More questions about anything? I'm going to be here all day. I think I've got an agenda where students can come ask questions, and my email's on there. It's kress@utk.edu. So if you want to talk about anything, feel free. I think it's on the first slide here, so you can feel free to contact me anytime and see me after or come to whatever session. All been great. I appreciate your patience. And sorry I was late. There's a big wreck. Dr. Pack, I was going to have a hard time getting to Knoxville, I can tell you that. But if you want to email me, kress@utk.edu, not a first initial or anything, because I got that when the internet started. So thanks again.
Any other questions? Well,
Thank you.